Hi, my name is Abigail, and today I'm going to be talking about my Physics Lab 3 macroscopic view of DC and RC circuits. So today in lab we're going to investigate both DC and RC currents using the Colorado FET simulator. We will experiment with light bulbs, resistors, capacitors, ammeters, voltmeters, and more. And the fundamental principles that we're going to be used in today's lab, just to name a couple: the loop rule, which we'll see in part 1, which is the sum of all voltages in any closed loop will be 0, and Ohm's law, which is voltage is equal to current times resistance. And then you can see the different equation variations when you finagle the formulas. And just a preview of our results: the resistance we calculated for the 47 ohm resistor was 48 ohms, and the 100 resistor was 102 ohms, and the RC we calculated was 6.13. So in part 1 we looked at a DC current, which you could see a picture of. It had 2 batteries, two ammeters. In some parts it had 1 ammeter, and some parts it has a voltmeter and others, and 2 resistors. The top resistor is a 47 ohm, the bottom is 100 ohm. You could see the graph with the change of potential differences, and this is a table of those as well. You can notice that in the table, the sum of all of the voltages ends up to be 0 volts. And our initial prediction for the current was 0.0204 amps. And you could see in the picture that the actual was 0.02 amps. And when you put the voltmeter on, it reads -3 volts and the current goes to 0 amps. And our resistance calculations, which I already mentioned, but I put how I got them: 48 ohms for R47, resistor 100, 102 ohms. The wire was 0 ohms and the ammeter was 0 ohms because when the voltmeter was attached to those locations, it was 0 voltage. So in part 2, we looked at the RC current, and which you could see in the picture here with the light bulbs. The light starts bright and gets dimmer over time. And so in the first part, we were experimenting with 10 ohm light bulbs and 20 ohm light bulbs. And you can see the charge time and the discharge time of the capacitor for each. Notice that the 20 ohm light bulb took more time to charge and discharge the capacitor. So the light starts bright and got dimmer. You could see in this picture the light is currently bright. And then in the second part, we used a 30 ohm light bulb and found the discharge time of the capacitor and graph the natural log of the voltage divided by the initial voltage versus time, and found the slope of that graph to be -0.163. And the slope is -1 over RC. So to find RC, we just did 1 divided by the slope, which is equal to 6.13. Now let's take a look at the what if. So the first what if was, if you're doing this experiment in real life and used an actual ammeter instead of an ideal simulated ammeter, what would happen? What's the difference? And so I'm going to say if we were using this in real life with a real one, there would be a slight resistance as opposed to 0 resistance that we experienced in the simulator, which would cause the running current to be slightly lower than we experienced. And for the second what if you were doing this experiment in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? And would this prediction happen in real life? Explain. Well, in our ideal model, the capacitor would be instantly charged. But if we made this circuit in real life, it would take a short time for the capacitor to be fully charged. And these results are because in the ideal simulator, there's no resistance in the wires and other components, but in reality, there is a small amount of resistance. Just like I mentioned in the first what if with the ammeter, there's just naturally a slight amount of resistance in each component of the circuit. Thank you for watching my Lab 3. Have a great day.